Howdy, in this example, we're going to talk about wear. Specifically, we're going to calculate the wear coefficients for copper and steel from data that was gathered from a pin and disc test. So what is a pin and disc? A pin and disc test is a very basic test that we can do to calculate wear rates of materials. So the setup is usually that you have a disc that is spinning, and then you'll have a pin to which we apply some force. The disc is going to spin for a certain amount of time at a certain revolution, and then when the test is done, we'll figure out how much of the material was worn away. So usually what we'll do is we'll weigh the steel disc or whatever material it is that we want to test. We will weigh the disc, we will weigh the pin before, and then we run the test. Material is going to get lost, so we clean the two parts very carefully again, and then we weigh the material one more time after it has worn away. So you can see here, if we look at like a little section right here from the disc, there's going to be a little groove from the pin, right, wearing away some of the material. And the pin as well, right, its length is going to shorten. So again, what we'll do is we'll measure the weights, and then we'll figure out how much weight was lost. And because we know the density from the starting materials, very quickly we can calculate the volume of the material that was lost by taking the mass, which we can grab from or calculate from the weight that we measured, and then divide it by the density, so we can get the volume of material, again, that was worn away. So in this example, specifically, we have a steel disc and we have a copper pin. There's a force of 20 newtons being applied. The disc is spinning and the copper pin is at a radius of 16 millimeters away from the center. And this disc rotated at 80 RPM, and it did so for 2 hours. After measuring the weight and calculating the volume, right, the book tells us that the volume loss for the steel was 0.65 millimeters cubed, and that the volume loss for the copper pin was 2.7 millimeters cubed. They also tell us that the hardness of the steel is 210 in Brinell scale, while the hardness for the copper was measured at 80 in the Vickers. So again, our job is going to be to calculate the wear coefficients. For this, we're going to use one of the wear equations. Now in class, we covered two of the equations, right? One for when we know the pressure, and then another one for when we know the force being applied between the two objects. So the one we're going to use is this one, where the volume of the worn material, millimeters cubed, is equal to the wear coefficient of the material that we're interested in, divided by the hardness. Now remember, the hardness has to have a special units of megapascals. This is going to get multiplied times the force between the two components. The force has to be in newtons in this case, and that gets multiplied times S, which is the total rubbing distance, and it has to be in units of millimeters. So we have the wear equation, and as long as we put the values in the correct units, very quickly we can solve for the K, which is the wear coefficient. When we solve for this K, for example, when we put the values of the hardness for the copper over here and the volume of the copper, we're going to get the wear coefficient on copper on steel. When we put the volumes for steel and the hardness of steel, that's going to give the wear coefficient for steel on copper. So we can solve very quickly this equation for the wear coefficient, K, right? It's just W multiplied times H divided by the force applied between the two and the total rubbing distance. So the hardness is given over here. All we have to do is convert it to the units of the megapascal. And to convert, we simply have to multiply either the 210 or the 80 Vickers, doesn't matter which one, by the factor of 9.81, and that's going to convert this into values of megapascals. Next is the force has to be in newtons. It's already in newtons, so there's not a lot of work that we need to do there. Usually the problem or the tricky part in this problem is just figuring out the total rubbing distance. So again, what's rotating here is the steel disc. The pin is stationary, it's just pushing down on the disc with a force of 20 newtons, right? So you can see, for example, that if we mark the starting point, if the disc does one rotation, right? For just one rotation, right, the total rubbing distance is going to be the circumference, where we're using this radius of 16 millimeters, right? So one circumference, or the circumference, right at the wear pattern, if you remember the formula for circumference, is 2 times pi times r. So in this case, it's 2 times pi times 16 millimeters. So let me plug it in the calculator. So this gives 100.53 millimeters. Now again, this is the circumference of this steel disc right at the wear mark over here. And this is just for one rotation. Now remember, the disc was rotating at 80 revolutions per minute, and it did so for 2 hours. So we're going to take one circumference, or 100.53 millimeters, right? It was this millimeters for just one rotation, or better yet, one revolution of the steel disc. If we multiply it now times 80, because it's doing 80 revolutions per minute, you can see here the units, we can calculate now how many millimeters of rubbing distance occurred now in 1 minute, because we have millimeters per minute. Now this thing went on for 2 hours, right? So let's go ahead and convert from minutes to hour, and in 1 hour there are 60 minutes, right? So now we can cancel this minute with this other minute, and if we multiply through, now we would have the total rubbing distance per hour, except that this test ran for 2 hours, so if we multiply times 2 hours, now the hours cancel. If we multiply all these numbers together, it's going to give us the total rubbing distance just in millimeters. So if we take 100.53, or the previous answer, times 80 times 60 times 2, it gives a total rubbing distance S of 96, or 965, I'm sorry, times 10 to the 3 millimeters. So now let's go ahead and plug this value onto this equation. Let me make some room. Again, W is the total amount of material worn away. So if we calculate first the wear coefficient for the steel on copper, we're going to use this value over here, 0.65 millimeters cubed. Next, we'll put the hardness of the steel, right? So we're calculating right now the wear coefficient for steel on copper. We'll put the hardness. This is nothing but the hardness, which is 210 times 9.81, right? And then this guy that comes out is going to have units of megapascals. Now remember, a megapascal is a Newton per millimeter squared. Now at the bottom is the force between the two components. This is 20 newtons. And then S is our total rubbing distance, which is 965 times 10 to the 3 millimeters. Now we know that this wear coefficient should be unitless, so let's make sure that all the units are canceling. So we have Newton on top, Newton at the bottom. This is going to cancel with this guy, right? We have millimeters cubed over here, multiplied times 1 over millimeter squared, right? So 2 of these are going to cancel. We're left with 1 on top. And then we have this one at the bottom. They're all going to cancel. So it's unitless. So again, we just type all of this in the calculator. We really need to make sure we pay attention to the units, that they're in the units specified. And that's it. So let's go ahead and calculate this. Is 0.65 times 210 times 9.81 divided by 20 times 965 times 10 to the 3. And this gives a value for steel on copper of 6.9381. I'm keeping a lot of digits after the decimal point. Times 10 to the negative 5. So next, if we want to calculate the coefficient for copper, right? We still have the same equation, but now we need to put the values for copper. So the volume worn away for the copper is 2.7 millimeters. And it's millimeters cubed, times the hardness. The hardness is given in Vickers, but if we take 80 and we multiply times 9.81, this is going to give the hardness in megapascals, or again, newtons per millimeter squared. All of this is going to get divided by the force, which is 20 newtons, and then the total rubbing distance over here, 965,000, or times 10 to the 3 millimeters. And again, we have 3 millimeters on top, 2 plus 1, 3 on the bottom, so the millimeters cancel. And we have this Newton canceling with this other one, so completely unitless. So again, if we type this on the calculator, 2.7 times 80 times 9.81 divided by 20 times 965 times 10 to the 3. And if I didn't make any mistakes here, or fat finger mistakes like I like to call them, we get that the coefficient is 1.0979 times 10 to the minus 4 for the copper. And again, specifically, it's not just the coefficient of copper, it's a wear coefficient of copper on steel. And this one over here is a wear coefficient on steel, but it has to be with steel against the copper. So as always, if you find any mistakes on my calculation, please let everybody know in the comments below. Otherwise, we'll see you on the next one.